Welcome. In this session, on the SVM, or support vector machine, we're going to vectorize the primal formulation. Recall that we had m inequalities, and so these m constraints, we can write these, if we take the original and multiply it through, what we get is it's yj times xj transpose times w plus b times yj, and that has to be greater than or equal to 1. This is, when we gather all of these together, what we can see is that that is the same as, so let's write that, that's the same as, we could say that so this for all j constraints will be x times w, and this for all constraints will be b times the y vector. And now for all constraints, we want the first constraint to be multiplied by y1, the second constraint to be multiplied by y2, and so on, and we can accomplish that with the diagonal matrix. And then this will be greater than or equal, and instead of a scalar, that will now be greater than or equal to the ones vector. And our objective, if we recall this from a previous session, is a function of the weights and the bias scalar, and that was 1/2 of w transpose w. And notice that in this objective, the bias scalar isn't present, and that's because it's present instead in the constraints. So the standard form of constraints that we have is we want it to be less than or equal to 0, so we have to bring these over to this side, and I'll write that as 1 minus yxw plus b times y, minus b times y, has to be less than or equal to the 0 vector. And now that is a property function that has a vector argument and a scalar argument and returns a vector. So we can think of this as a vector valued function. When we take these together, we can now form the primal Lagrange function. And so this primal will look like a Lagrange function that has the vector argument, the bias scalar, and now we'll represent the Lagrange multipliers using alpha, because that's what most SVM literature does. Previously we would have used lambda. Now we'll use alpha simply so that it's easier for us to read other material, and that will be 1/2 of w transpose w plus, that'll be alpha transpose times the property function, which is 1 minus yxw minus b times y. And let's observe that this term is alpha transpose 1. That could also be 1 transpose alpha, and this term is the sum of the Lagrange multipliers. This term, alpha transpose y, is the same as y transpose alpha, and that is the sum of the product of the label and the Lagrange multiplier. So to find the dual, we need to differentiate. Now, when we do the differentiation, to find the dual, we don't have to differentiate with respect to alpha, because what we want to do is we want to eliminate w and b from this expression. And the way that we do that is we find the partial derivative of the Lagrangian with respect to the weight vector, and that will be 2 times 1/2 is, that'll be w transpose, and then this will be plus alpha transpose yx with a negative sign, so that'll be minus alpha transpose yx, and then that's constant with respect to w, and that's constant with respect to w. The next differential we need is the derivative of the Lagrangian with respect to the bias scalar, and that will be 0, 0, 0, and now that will be minus alpha transpose y. So that is minus alpha transpose y. And the Lagrange equation is, so the Lagrange equations, or equation, this is we can think of it as a single linear system, is we'll take the partial derivative of the Lagrangian with respect to the weight vector, and we transpose that from a one form into a vector, and then we take this partial derivative with respect to the bias scalar. Now that's a scalar, but let's be formal and we'll transpose that. And then this entire matrix or vector value, this entire vector valued object is a function. It varies with the weight vector and with the bias scalar. And we want to set that entire function equal to 0 at the stationary point. And when we solve this, we can solve this part by part. Is that what we can conclude is that from the first part, what we have is that we now have requirements, and we would, if we were trying to find the optimal weight vector at this point, we'd put asterisks in. But now we'll simply say that at a stationary point, whether it's an optimal stationary point or not, we know that if this equals 0, then that means that the weight vector, when we transpose this, the weight vector has to equal, and this would be the transpose, so that would be x transpose, and then y transpose. Oh, but y is a diagonal matrix, so y equals y transpose. So I can just write y, and then times the vector Lagrange multipliers. And from this, that equals 0, and what we'll do is we're anticipating that we want alpha to be a vector for subsequent substitutions, and so alpha transpose y is just alpha dot y is y dot alpha is, we can say y transpose alpha has to equal 0. And this says that we can now substitute, we now have a formula for w that depends on the data vectors, on the labels, and on the Lagrange multipliers. And here we have a constraint on the labels and the Lagrange multipliers. That is, when we take each label and multiply it by each Lagrange multiplier and add them all up, they have to equal 0. This is the term that we'll substitute into the primal to get the dual, and this we'll use to simplify our equation.